Hello everyone, welcome to the last lecture of week 6 of the course Power Network Analysis, in which we will continue our discussion on different transmission line models and the use of these models to understand their performances. In today's discussion, we will specifically look at what is meant by surge impedance loading. When do we say that a line has been loaded to its surge impedance? So what exactly is surge impedance? We'll understand that. And then we'll also try to understand if at all, if there is any similarity between the complex power flow expressions in these transmission lines with respect to the power flow expressions that we have seen in context of synchronous generators and so on specifically. Till the last lecture, we had discussed about the long line model, specifically the lossless long line, in which we understood that the voltage and current in a lossless long line can be interpreted as waves, similar to the waves that exist in water or in a pond when a pebble is thrown in the pond. So similar interpretation about waves, what do they exist there? The similar notation or philosophy can also be there for voltages and currents in a lossless long line. And since these can be interpreted as waves, we can also have definitions of the corresponding wavelength and the corresponding velocity at which these waves propagate. In fact, the waves that propagate in transmission lines, they are essentially electromagnetic waves, and this is the reason or primary reason how power generated from transmission stations or transmitting sources is fed to the transmission lines, and then it reaches the corresponding loads. And that's the reason why when we turn off or turn on a switch, our appliances get on and off without any delay to the human eye, visible to the human eye, because the speed or velocity at which this energy gets propagated is almost equal to the speed of light in vacuum. And in fact, if this speed were to be associated with the speed of flow of electrons in a particular conductor, our transmission lines are also made of particular conductors, then actual electrons, they will never ever travel at such high speed, because Einstein's theory of relativity would then come into effect, where the electron will no more remain as an electron, it would become an energy. And in fact, the electrons, they dissipate around their mean position, and that speed or the rate of dissipation is much slower than the value of u, which is there for a practical transmission line. Also, for a lossless line, the corresponding attenuation constant would be 0, whereas the phase constant would only depend on the per unit inductance L and per unit capacitance C for a given transmission line. We have also seen these equations for lossless long line, where the reference position or the distance is being measured with respect to the sending end. X is the line length, and at any point x at in the transmission line from the sending end, the corresponding voltage and current expressions in terms of sending end voltage phasor Vs and sending end current phasor Is. Vs and Is, they are phasor quantities. In terms of these phasor quantities, we can also find the corresponding voltage and current at any point x in the transmission line. Zc is the characteristic impedance, and beta is essentially the phase constant which we saw in the previous slide. So if the line length is indicated by LL and the receiving end is at a distance LL from the sending end, then essentially if we put x is equal to LL in the above expression, we would essentially get the receiving end voltage, which is equal to the voltage at x is equal to LL, and similarly the receiving end current phasor IR is I at a value of x is equal to LL. So we will be able to get VR and IR, the receiving end phasors with respect to the sending end phasors. And since our transmission line follows the property of symmetricity, reciprocity, so the determinant of this particular matrix is not 0, it is not a singular matrix, and hence it can be inverted into this matrix, wherein we can also find the sending end quantities in terms of the receiving end quantities. Coming to the surge impedance loading, we infer or call a line to be loaded at surge impedance loading when the load itself is equal to the characteristic impedance of the line. That means if I have a transmission line which is represented by this two-port network, we have talked about two-port networks at length, and if I denote sending end as voltage as Vs and sending end current as Is, and similarly the receiving end quantities are IR and VR correspondingly. I would call this transmission line to be loaded at surge impedance loading if I connect a value or an impedance, let's say ZC, where ZC is the characteristic impedance, and if this load is connected to the receiving end, that means the load is feeding a load which is called as the surge impedance load. That's the very basic essence. And by KVL across the receiving end, we get this particular voltage equation where receiving end voltage should be equal to the voltage drop across the load which is connected, and ZC is the characteristic impedance, which is the surge impedance itself. For lossless line specifically, in fact, for general loading of line, we always tend to define the line loading in terms of percentage of SIL, few X percent, Y percent of SIL. For a lossless line, the characteristic impedance has a very unique attribute. In the sense, for lossless line, the per unit line resistance is 0, per unit line conductance is 0. What is not 0 is the per unit line inductance and the per unit line capacitance, and hence ZC, which is the characteristic impedance, which is nothing but root over of L by C, turns out to be a pure resistive number, a pure real number, not a complex number at all. In general, for long line, characteristic impedance would be a complex number. For lossless line, it turns out to be a purely resistive number. So for surge impedance loading of a lossless line would infer that ZC, which is appearing over here, would be a pure resistor. It is a pure real number, so there is no complex part associated to it. And for this specific case, for SIL at lossless long line, there happens to be a very interesting phenomena which we will understand. So let's go deep into that. So for a lossless long line, as per the ABCD parameters of lossless long line, we can represent Vs in terms of VR, IR. We have known what are the values of ABCD, so from there we can get these values. And since the lossless line is loaded at surge impedance loading, which is nothing but ZC load connected to the receiving end over here, and VR is equal to IR ZC as per the KVL. So this term here can be rewritten as VR, wherein we get this particular expression, which essentially says that Vs is nothing but VR into e to the power j beta LL. Beta is the phase constant, J is the complex operator, LL is the total line length, and beta is 2 pi f root over of LC, which is again a dimensionless quantity. So essentially, what we are getting here is that, so in fact, beta into LL is a dimensionless quantity. Its unit is in radians or could be converted into degrees for the sake of evaluating e to the power j beta L. So if we recollect, e to the power j theta, where theta is some angle in degree or radians, it is equal to cos theta plus j sin theta. And if we have to find the magnitude of e to the power j theta, it would nothing be but cos square theta plus sin square theta entire root over. Cos square theta plus sin square theta is always equal to 1 irrespective of value of theta. So essentially the mod value or magnitude is always equal to 1. So what I am trying to say is that this quantum over here, sitting over here, it can have its own phase shift, which is nothing but beta into LL. The value of theta or beta LL can change as per the line length, but the magnitude will always remain 1, which means if the magnitude of receiving end voltage is known, the same magnitude would come up with the sending end voltage also, although there could be phase difference between sending end voltage and receiving end voltage, which would nothing be but this angle beta LL. Similarly, for the sending end current, if we substitute those numbers, so basically VR by ZC is nothing but IR. So that's how we get IS is equal to IR into j e to the power j beta LL. In fact, if we try to find voltage and current at any distance x from the sending end, then as per the lossless long line model expression, Vs and Is can be used to find the corresponding Vx quantity. If we substitute these numbers, so let's say if we put Vs as Vr e to the power j beta Ll over here, and if we put Is as Ir e to the power j beta Ll, where further Ir into Zc is equal to Vr, we get an expression of this form, which again, by using the fact that e to the power j theta is cos theta plus j sin theta, if we combine these two aspects, we get Vx in terms of Vr, where we again have a quantity e to the power j some angle, which is beta Ll minus x, whose magnitude is always equal to 1. The phase angle can change as per the line length. Similar analysis or similar expression can also exist for the current at a distance x from the sending end. So essentially, since the magnitude of this exponential quantity is always 1, irrespective of the value of x, the magnitude always remains 1. That means at any point in the line, which is loaded at, which is a lossless line and loaded at surge impedance loading, the voltage magnitude will always remain the same. The current magnitude will always remain the same. The phase angles of these phasors can differ as per the distance x, but the quantum or the voltage magnitude, let's say if the receiving end voltage is at 500 kV, the same 500 kV would be present at every point in the line. The phasor of this 500 kV may be different depending on the line length. Similarly, if the receiving end current is few thousands of amperes, the same current would flow at every point in the line. The phasor quantity or the phase might be different. So that is what is the beauty or specificity about a lossless long line loaded at surge impedance loading. The magnitude remains the same at all points irrespective of the length x. And so because this happens, so there has to be a reason why the magnitude of voltage is same, why the current magnitude is also same, and so on. What happens is, when we are focusing or talking about a lossless long line, if you recollect our previous discussions, lossless long line has a per unit line inductance L and a per unit length line capacitance C. What happens when the line or lossless line is loaded at surge impedance loading? The inductor of the line inductance, which is present at every line length. In the distributed model, actually everything is distributed. So every small minuscule section of the line length has some inductance. The same section might also have some capacitance C. What is happening is that for every such smaller minuscule section or distributed section, the reactive power which is being generated by the line capacitance, the same power is in a way getting absorbed by the line inductance when the line is loaded at surge impedance loading. So in a way, the actual line is not consuming or delivering any reactive power. The overall reactive power generated by the line capacitance, which is a reactive power source, the entire component of it is getting absorbed in the line inductance, which is a reactive power absorbing quantity. And that's the reason why the net reactive power supplied by line capacitance at each point is equal to the reactive power absorbed by the line inductance. There is no reactive power flow to the load in the situation when the lossless line is loaded at surge impedance loading, because in that case the load itself is a pure resistor. Zc is a purely resistive number in case of a lossless line, and hence there is no need of reactive power at the receiving end. The entire line does not consume any net reactive power, not does it deliver any reactive power. And furthermore, if we substitute our receiving end voltage and receiving end current in the expressions which we have seen earlier, we can get the voltage and current at any distance x from the sending end perspective. So here, in this case, if we have this lossless line where we have seen what happens when the line is loaded at surge impedance loading, there could also be certain specific cases where the line is open circuited. That means if the line is open circuited, there is no load present at the receiving end, which would refer to 0% of surge impedance loading. So for open circuit case where the line load is 0, there is no load present at all, that means the line receiving end is open circuited, so receiving end current would become 0. If receiving end current becomes 0, that means this quantity is gone here, this quantity is also gone, and we have only left with Vx is equal to Vr cos of beta Ll minus beta x. Now let's look at the value of this V of x as x is increasing or decreasing. At a distance of x is equal to 0, the x distance is being measured with respect to sending end. So basically, V of x is equal to 0 would refer to value of V of s, which would be equal to Vr cos of beta LL. This is one condition. And then at the extreme condition, we have x is equal to LL, which refers to the receiving end voltage being measured from the sending end. So we have Vr, which is again equal to Vr because cosine of 0 is equal to 1. So we have only Vr. And depending on the value of beta and LL, so no matter what this beta LL value is, cos of theta is always less than equal to 1. In fact, its value ranges between -1 and 1. So if we basically take its magnitude, what we see here is that for the sending end voltage when the line is open circuited, the sending end voltage will be less than the receiving end voltage magnitude, in terms of magnitude only if we say, because cosine of angle will always be less than equal to 1. So if we put that expression here, we have sending end voltage less than the receiving end voltage. Isn't that a bit strange that our receiving end voltage tends to be boosted up compared to sending end voltage, where sending end voltage or sending end source is the actual source of power? So this phenomena exactly of receiving end voltages getting boosted up or amped up under light loaded condition is nothing but the Ferranti effect. What is essentially happening is that under light loaded conditions, the receiving end voltage is more than the sending end voltage, which means that the reactive power which is being generated by the line capacitance, not all of it is getting consumed by the line inductance, because there is no load at the receiving end, it is open circuited. So more reactive power is being consumed generated by the line capacitance, and lesser of it is being consumed by an inductance. So essentially, at the receiving end, we have a lot of reactive power which is going nowhere, which in a way results in increasing the receiving end voltage. That's the basic phenomena. Similarly, under short circuit condition, where the line is entirely dead short circuited, so receiving end voltage would become 0, and consequently we would have sending end voltage V of x as expression of I of r. Now in this case, as we see the value of x or impact of x on the voltage itself, we would observe that at the receiving end, the voltage magnitude is at its minimum and the value is at the maximum at the sending end. The voltage in a way is meaning that the sending end voltage would always be more than the receiving end voltage when the line is short circuited, which means that more reactive power is being supplied. So lesser reactive power is being absorbed for loading less than SIL, and exactly vice versa case is happening in case when the line is loaded more than the SIL or higher loading, which means that more reactive power is demanded from the sending end, so receiving end voltage has to be lower so that corresponding compensation can happen. This plot here essentially shows the variation of receiving end voltage and the sending end voltage and receiving end voltage as a function of line loading. Usually the line load is represented as percentages of SIL. So no load condition here would refer to 0% SIL, whereas short circuit condition would refer to infinite percentage of SIL. And at SIL, as we have discussed, the voltage profile is completely uniform, the magnitude doesn't change at all. Generally, for light load conditions where load is less than the surge impedance loading, which means more reactive power is being generated by line capacitance and lesser of it is being consumed by the line inductance, to maintain the voltage at the receiving end, which is in a way indicating this particular section where receiving end voltage is more than the sending end voltage, we would essentially need some device which can absorb this excess of reactive power at receiving end and try to bring back this receiving end voltage closer to the acceptable norms of the voltage as per the sending end. So in those cases, we would essentially connect some shunt inductors at the receiving end so that the excess reactive power can be absorbed by these shunt inductors, and vice versa. When the line load receiving end voltage profile is very poor, we might need some device like capacitor or reactive power generating device which can boost up the voltage profile at the receiving end, and hence we use shunt capacitors for voltage compensation. Usually lines are loaded way beyond their surge impedance loading to maximize their utilization and increase the overall transfer capacity. So essentially, in majority of compensation aspects, we would often find the use of shunt capacitors mostly in being used in transmission lines, because line loading is obviously going to be more than the actual SIL. So we need some shunt capacitor to increase the voltage profile by adding more reactive power resource at the receiving end. In terms of complex power flow through the line, we have understood about different line models. We have figured out ways of how to find ABCD parameters for short, medium, long, lossless line, etc., etc. So we have one such transmission line where the ABCD parameters are known as per the discussion that we had with respect to different two-port network parameters. ABCD parameter is one such representation of two-port network parameter. And we are trying to find the expression of sending end and receiving end powers. By powers, I mean complex power, real power, reactive power. So what I have is, I have a transmission line whose ABCD parameters are known, and I'm choosing the receiving end voltage, per phase voltage as a reference, and sending end voltage is also being measured with respect to receiving end. So the sending end voltage is leading the corresponding receiving end voltage by an angle delta. The notion of why delta has been used here is to bring in some correlation with respect to the delta that we saw for synchronous generator, which was the torque angle there. But the notation can be different. The meaning or the representation is important here. And we also know our ABCD parameters. Usually for transmission line, these are complex numbers. So we can represent these A and B's. You can also do the same for C and D. But A and B's, they are complex numbers. So I'm representing them through polar coordinates. And remember, by reciprocity or symmetricity, A is equal to D. So if we know the value of A, D would have the same value. And we also know that AD minus BC is equal to 1. So if we know A, D, and B, we can indirectly also find C. And that's the reason why I have not explicitly defined C and D here, because by symmetricity and reciprocity, we can find those values. And now if we put in those numbers or the representation here, so VR is VR at an angle 0, IR is to be known in terms of VS and VR, so we can get a complex expression of IR in terms of A, B, VS, VR parameters. Similarly, we can also find the sending end current expression in terms of these A, B, VR and VS parameters. And having known the receiving end voltage, receiving end current, which is the expression over here and the expression over here, we can find the corresponding receiving end three-phase complex power, which is 3 VR IR conjugate. So if we plug in those numbers carefully, we would get this expression, which is the complex power expression at receiving end. We take the real part and reactive part out of it, real and imaginary part basically, so we get the real power expression and reactive power expression. Similar analysis or expression could also be obtained for sending end complex power, sending end real power, and sending end reactive power. If we reorient or rearrange things a bit and try to bring in the aspect that usually the voltages at sending and receiving end, they can be maintained, regulated, controlled by proper compensation devices, which we will see in the next lecture. So usually VS and VR, they are controllable, regulatable quantities. So we can assume them that they are often going to be constant. The magnitudes are often going to be constant. What might change is the angle delta, which is between sending end with respect to receiving end. For a given transmission line, ABCD parameters would also usually be fixed. So essentially, the only variable that might appear in these different expressions is the angle delta only. VS and VR, we generally assume them to be constant, or they can be made constant through proper compensation. So we can rearrange these terms so that we can get the receiving end powers and the corresponding sending end powers through some simplicity or rearrangement, so that our unknown term, which is the term present with the angle delta, retains on one side, and all other known quantities, they are present on one exact side. So essentially, if we rearrange the first two expressions over here, basically I'm trying to bring in this negative term on this side, this negative term over this side, and I'm only left with the complex term, or the cosine theta and sine delta term on the right hand side, with the fact that I'm replacing the receiving end phase voltage and sending end phase voltage in terms of the receiving end line to line and sending end line to line voltage. So I get this expression. Here, if we look at the expression, what we get is that, let's say if I square up this entire term, I square up this entire term and then try to add them up. What I would observe is that I'll have PR plus A VRL square by B cos theta B minus theta A whole square. Similarly, for QR plus A VRL square sine theta B minus theta A by B whole square will essentially be equal to VRL square VSL square by B square, because cos square and sine square, they add up to 1. And if I sort of expand my imagination, there is also a similarity between the term over here and the term over here. Essentially, in complex plane, if I were to mark this equation, which is this locus equation, on a complex plane where P is on x-axis and Q is on the y-axis, then this equation essentially represents the equation of a circle whose radius is VRL VSL by B, and the center is minus of A conjugate divided B conjugate VRL into VRL conjugate. Why am I saying A conjugate B conjugate? Negative sign is because general expression for circle is x minus A whole square plus y minus b whole square. If it is r square, then on xy plane, A comma B becomes the center and r becomes the corresponding radius. That's how the center circle equation looks like. So similarly, if I am trying to simplify or relook at things from the complex perspective, A conjugate, if you remember, our A was A at an angle theta A, whereas B was, which was the complex number again, B at an angle theta B. So if I put those numbers here, I have minus A mod by B mod at an angle theta B minus theta A, because B conjugate is mod of B at an angle minus theta B, which when taken up on the numerator becomes plus, multiplied by VRL was simple VRL square, so the mod comes over here. And if I take the cos of this term, I have the term over here. If I take the sine of this term, then I have the term over here. That's how the circle or the locus looks very similar to the locus of synchronous generators, which was capability curve. The locus of complex power at receiving end is a circle. For varying delta, it's a circle on PQ plane with center as this coordinate and radius as this coordinate. Similarly, if we relook at the sending end quantities, then we have a similar circle with a difference of center. The radius remains the same. That's all for today's discussion. We will take up the discussion of reactive power compensation, which is going to be the last lecture for this particular module and the first lecture of week 7. Thank you.